Hello, everyone. My name is Keegan, and I'm a master's student in ECS and CCI. I appreciate your attention to the research I'll be sharing with you today on the subseasonal variability of temperate snowpack properties across the Juneau Icefield using multi-offset ground penetrating radar. I want to acknowledge that this work wouldn't have been possible without the rest of the UMaine Polar Geophysics team, the Juneau Icefield Research Program, the University of Colorado at Boulder, the U.S. Army Corps of Engineers Cold Regions Research and Engineering Laboratory, CCI, and ECS. I also want to acknowledge that the research I will be presenting today is conducted on the unceded territories of the Haida and Taku River Tlingit people on Tlingit and I. We acknowledge that the Haida and Tlingit peoples have been stewards of the land on which we work and reside since time immemorial. We're grateful for their knowledge and stewardship. And also, if you would like to learn more about the lands you work and reside on, please check out the free interactive map on native-land.ca. All right, so you're probably wondering why you should care about snow. I know it's annoying to drive in and shovel, but it's an important global resource. For starters, meltwater from snow provides fresh drinking water to over a quarter of the planet's population. This meltwater also impacts downstream ecosystems, where it provides fresh, cold water and nutrients to warming streams that host keystone species such as Pacific salmon. It's also an important component of glacier mass balance, where annual snow accumulation adds mass to glaciers and enables them to grow and flow. Additionally, I'm sure most of us were around when Maine experienced catastrophic flooding in December 2023 and January 2024. Understanding how much water is held within a snowpack at a certain time and how that water content varies over space and time can better inform flood forecasters. So, my research is focused on a non-polar ice field in Southeast Alaska called the Juneau Icefield. Like most other glacier systems in Alaska, the Juneau Icefield is also losing mass much faster than any other mountain glacier system in the world and is contributing significantly to sea level rise. It's about 4,000 square kilometers in size and stretches from coastal Alaska to interior Northwest British Columbia. It's been an active area of research since the 1940s through the Juneau Icefield Research Program. The data I will be sharing with you today will be from the blue line, also known as the Divide Transect, and the two end-member cores drilled by our friends at UC Boulder, known as MLD and TKG4. The other black lines on this map represent the other data acquired during this research campaign in June 2024. So let's dive into some ground penetrating radar basics. Here I've displayed what's known as a common offset system, where we have a single transmitter and receiver. The transmitter emits electromagnetic energy into the subsurface. In this case, I've shown a glacier, and this energy reflects off of layers that have different electrical properties and then back to the receiver. The electrical properties can be defined as the material's permittivity, and contrasting permittivities found within a glacier system can significantly impact our ability to effectively image the subsurface with radar. Water, for example, has a permittivity that is approximately 30 times that of wet snow and fern. This causes significant attenuation of our radar signal, as shown in the radargram to your right. Here, high water content in the wet snow zone turns our beautiful stratigraphic horizons to TV static. So, water content within snow can significantly impact our ability to image the subsurface with radar. And now that we know the basics, let's complicate things. Remember the common offset system I showed in the last slide? Well, the multi-offset system Kaylee Manello and I used for this research is 16 times more powerful than a single common offset system. This is because it consists of multiple different transmitter-receiver pairs, 4 transmitters and 4 receivers, all together combine to show us 16 different individual common offsets. In this diagram, I show our system and an example of a shot gather, where the first transmitter in the array sends energy into the snow, and this energy reflects off of an ice lens and back up to the receiver at a midpoint distance between that transmitter and receiver. When you run this through all of the transmitter receiver pairs, you can effectively measure the spatial variability of how fast that energy travels, also known as the radio wave velocity. It also increases our signal to noise ratio. It's similar to writing a paper by yourself and then having 15 other people review and edit it for you. And this is my favorite part. Tate Meehan from Corel developed a 20-meter long linked sled system called the Big Multi-Element Sled System, or Big Mess for short. This monster hosts are 8 antennas at varying offsets, ranging from 1 meters to 20 meters in distance, and it's towed behind a snowmobile at painfully slow speeds. Here are some photos of Kaylee and I putting it together, surveying at the MLD core site, and a beautiful drone view of the mess from Erin Towns. And now for some results. The focus of my thesis work is on a repeat survey of the divide line, from the center of the ice field to the high ice divide, which were collected 1 week apart. This figure shows the elevation profile from each transect on top with the stacked radar grams below. Can you see any changes between the two radar grams? Well, if you're having some trouble seeing, I highlighted some for you. Here, I've interpreted the firn ice transition and annual accumulation layer in the center panel. The orange box highlights the upper portion of the transect as we transition from a lower elevation ablation zone to a higher elevation accumulation zone. In some areas, we see increased reflections from stratigraphic horizons from the snowpack, while there is a dampening effect or more signal attenuation closer to the end of the transect in some of those deeper layers. I've also included some photos of Tate during our survey to show how beautiful, sunny, and warm it was. From the multi-offset system, we can estimate the stacking velocity, or the bulk velocity, the interval velocity, or the average velocity of a layer, the dry density, permittivity, wet density, and liquid water content, the entire depth profile across the transect. Here, I'm flipping between the models from our first and second acquisitions. The velocity models are measured directly from the radar, while the permittivity is calculated directly from the interval velocity. Dry and wet densities and liquid water content are computed through a two-phase dielectric mixing model called the complex refractive index method and contains inputs from our in situ core measurements. And here, I've quantified just how much each of these variables have changed over the course of a week and where that change occurred. Overall, we see minimal variability in the minimum, mean, and maximum values for each variable. However, all of these models show the greatest change in the snow in the lower elevation ablation zone. And additionally, wet density and liquid water content changes appear to be centered around the firn ice transition. GPR is great and all, but our data needs to be ground truthed. Dr. Bradley Markle, Dr. Annika Horlings, and Juliana Roof, along with the help of Kaylee, Mari Fromstein, Tahi Wiggins, and others, drilled several firm cores and collected density and permittivity measurements. From these data, we can calculate velocity and liquid water content, all of which are used to constrain our radar-derived estimates. Here, I've shown an example of what our permittivity data looks like plotted against the permittivity measurements from the core. Safe to say that we pretty much nailed it. And that is about all I have time for. Thank you for watching. If you have any questions or comments, feel free to send me an email. Thank you.